Okay, the last class we had discussed about module ports declaration, what is meant by module, what are the functions we are writing in the module, and then how we are connecting input output ports from the design to external world like test bench, and then ports declaration, how the module is designed with the hierarchical modules. So all these things we have discussed.
Yes, sir. Sir,
Similar.
what is the meaning of hierarchy?
Hierarchical means, see, first module is there, second module is there, multiple modules are there.
Yes.
Okay, so each one is related. For that, we are designing one top module. That top module having all the module instantiations. So that is related to hierarchical modules. So in this way, we are designing complex of what multiple modules we are designing, because module does not allow inside the module representation. One module is there, inside another module you are writing means that is not allowed.
Yes, sir.
So module instantiation should be allowed. So that means four modules are there. Four modules having different functionalities. Okay, those functionalities I want to represent in one area. I need to integrate all the modules.
Yes.
So that is called as hierarchy module. Okay, so that is called as, sometimes we can call it as top module, or sometimes we can call it as a wrapper. All these things we are calling. So these are the test bench components. What are those? Um, Module instantiation, and then in that instantiation we are following the ordered based or name based, or test bench declaration of ports, and then initial begin block, inside that dollar monitor, and then display statements. All the initial all the signals will be passing, that means stimulus we are passing, and then clock generation we are doing that by using the always at the rate. So we go for the clock generation. After that, end module, how we are ending the module means dollar finish we are using, and then end module. So this is the test bench writing in our Verilog. These are the things we need to mention in our test bench, must and should.
Yes, sir.
So gate level modeling. Okay, gate level modeling is related to whatever the gates we have, right? Logic gates,
Yes.
and gate, or gate, not gate. All these gates are interconnect them. Okay, so that means we need to represent two gates. In between that, there is a interconnect. So we need to connect these two gates. So this is the lower level of abstraction. Okay, so in terms of design, by using gates, it should be the lowest priority. Sometimes we are using, because in our modules the inbuilt operations are there. These are user defined primitives. Okay, UDPs, AND gate, OR gate, XOR gate, NAND gate, NOR gate. All these gates are user to see. These are the buffers. Okay, so there is a control signal. So based on the control signals, this is low signal, and then sometimes high signals will be there. Okay, this is not there. It is given by the just buffer symbol. So then there is a control signal is there. Buffer 0, buffer 1. 0 means there is a control signal lower value, and then not if, that is also having control. 1 means high level, and then 0 means low level value. Okay, this is not this is the not gate, not buffer.
Yes.
Not if operation. That means not if means we are giving some control signal 1. Okay, so if the control signal is 1 means you are giving 0, input is 0, then it is converting to inverting operation. If the control information is 0, then input is unknown value you are giving, you are getting unknown value. So because uh, unknown, not a unknown value, high impedance value we are getting, because inverter you are giving the unknown value means what type of output I am getting. So the wire default value we are getting high impedance value. Same way, not if value we are getting unknown value you are giving, and then control signal also 0 you are giving, means that is not operating condition you are getting.
In front of NAND gate, that circle symbol is enable bit, sir.
See, NAND gate, whatever the AND gate is there, that AND gate having the NOT gate. Okay, so this NOT gate is called as bubble. Okay, so
Okay.
then it is called as NAND gate. Okay, and followed by NOT gate, that is called as NAND gate. Okay, so AND gate, OR gate, XOR gate, NAND gate, NOR gate. See, NAND, NOR are universal gates. Okay, and then AND or NOT are basic gates.
Yes.
Okay, exclusive OR gate is the special purpose gates. XOR gate, XNOR gate, this is the special purpose gates.
Actually,
Okay.
many don't know that small things. Bubble.
Mm.
Actually, they know it, but specifically they don't know that is bubble.
Yeah. Bubble means, so NOT gate. So that means OR gate is there, right? So this is the NOR gate. Okay, OR gate is followed by NOT gate. Then we can we can convert into NOR gate. So this bubble will represent that NOR gate representation.
Yes.
Okay.
Then how enable pin symbol will be, sir?
Here, gates doesn't have any enable signals because we are not, see, combination circuits means continuous assignments. Immediately we are giving the input means immediately I am getting the output.
Yeah,
So,
that I know. Generally, I'm asking how enable pin symbol.
so enable signals, we are having some combination circuit like encoder, decoder, multiplexer, demultiplexer. At that time, we have an enable signal because they are depending upon that switch. If you on the switch means it is giving the input. It is output is depends upon the input, and then we are getting some output.
Yes, sir.
And then these gates are not depending upon any enable signals. Okay. See, AND gate operation, how we are representing the syntax of gate. So, AND some gate representation, or AND 1 or 1 XOR 1. So, in that way, I want to represent that. Same, your gate is representing here, and then name you need to represent. So, that is represented with G here. Okay. So, first we need to represent the output, comma, number of inputs. Input 1, comma, input 2. Okay, in this way we are representing input 1 comma input 2. So this is the syntax for all the gates. Whatever the output you need to represent, suppose this is my output. Okay, OR gate is there. This is my OR gate. A, B are two inputs. Y is an output. So then OR1 I am representing my name. Okay, output Y comma input A comma B. In this way, both are depend. Output is depends upon the inputs. Okay, if the A B values are changing and you are getting the output value is Y. Okay, so see, all the syntaxes are same. Output comma input 1 comma input 2. Output comma input 1 comma input 2. So NAND gate, NOR gate, XOR gate, buffer. Buffer is depends upon the output comma input. So whatever the input we see, this is the buffer, right? So we are giving input, okay, and then output we are getting. Whatever the input you are giving, same output we are getting. That is the buffer. Okay, so that's why input, output comma input we are representing. And similarly, NOT gate also we are having the output comma input. Okay, so output comma input means you have NOT gate. This is my NOT gate. Okay, here inverting operation is there. If you are giving 1 and I am getting 0, if you are giving 0, I am getting 1 here. Okay, buffer if. Okay, buffer if means it depends upon the control signal. If the control signal is 0 or 1, then only the output will be getting at the input will be getting at the output side. Okay, so input will be getting output side depends upon the control signal. See, if buffer buff if 1 means this is the control signal high. If the control signal is high means then only the buffer is input, whatever the input you are giving, that is appear at the output side. See, one you are giving control signal, your input is 0, output is also 0. You are giving 1, your input is 1, output is also 1. If your control signal is 0, then input is unknown value, anything, either 0 or 1, but I am getting the output is high impedance only.
Yes.
Okay, and similarly buffer if control if 0 means this value will be operating at the low level. Low level means the control signal, whatever the control signal is there, if you are giving 0 then only it is a operating condition. If you are giving 1, so it is not in operating condition. See, if you are giving 1, you are giving any input either 0 or 1, your input this is the buffer if I am having the low level control signal. Okay, this is my control signal, input I am giving and output I am getting. Okay, input 0 you are giving, control signal is also 0, then your output should be 0. Or control signal still 0, your input is 1 and my output is 1. Now control signal is changed to 1. Your input may be either 0 or 1, but I am getting the output is high impedance only.
Yes.
Okay, that is the buffer if. And not if it is also same, but you are getting the output is inverting operation. Whatever the input you are giving, same operation, your control input is 0, then input is 0 means output should be 1. Okay, because not gate, right? Your control signal is still 0, your input is 1 means output should be 0. And then your control signal 1 means whatever the input you are giving, I am getting the output is high impedance only. Okay, clear? So this is the gate level representation. These are the truth tables, you know, right? AND gate operation. What is the AND gate operation? If both the inputs are 1, both the inputs are high, output is high. Any one of the input is low, output is low for the AND gate. OR gate, if any one of the input is high, output is high. If both the inputs are low, output is low. That is the OR gate. And NOT gate, you are giving a 1, output is 0, complementing the input. You are giving 0, you are getting the output is 1. Okay, and then NAND gate, that is the complement of AND gate. So both the inputs are any one of the input is 0, any one of the input is low, output is high. If both the inputs are high, output is low. Okay, NOR gate means if any one of the input is low, output is low. Okay, sorry. If both the inputs are low, output is low. If any one of the input is high, output is low.
Yes.
That is the NOR gate. And then exclusive OR gate means if both the inputs are same, output is 0. If the inputs are different, output is 1. Or odd number of ones is present there means your output should be 1. Okay. And exclusive NOR gate means if both inputs are same, output should be 1. If the inputs are different, your output should be 0. These are the gates. And same way, I have represented some example module name, and ports list. In that, input 1, input 2, control signal, and then outputs are AND gate output, OR gate output, NAND gate output, NOR gate output, XOR, XNOR, buffer, NOT gate, buffer if, not if, buffer if 0, not if 0. All these are outputs. So then my gate is AND gate. My AND gate name is A1. So my output of AND gate is O AND. Okay, that is the output of AND gate. Inputs are I1 comma I2. Same way, all the gates you need to represent. Okay, buffer if. Okay, my output is buff if 1. Okay, my gate name is BF1. So buffer if 1. Okay, the control input is input, and then one input we are giving, that is I1. Okay, in this way I am representing different values. Okay. Uh, these are the gate level simulation. See, all are primitives. Verilog supports predefined gates, that is commonly used as a primitives. All these are primitives. Okay, user defined primitives are all these things. And then delays in your gates, because all the primitives we are having the gates. And then see, buffer if you are not if provide any input and you are getting the output as a high impedance value, right?
Yes.
Either buffer if 1 or buffer if 0, both are getting or not if 1 or not if 0, you are getting high impedance value only. If you are not giving, the control signal should be 0 or 1. Okay. And different type of delays we are having: rise time delay, rise delay, and fall delay, and turn off delay. Rise delay means you are giving some input, okay, and then you are getting the output some delay. See, this is the delay. That means rise delay means it is starting from 10% to 90% reaching. Okay, 10% to 90% reaching, because we are not getting exactly 0 and 1 is not changing exactly at the 0 time only. Okay, it is taking some time. Okay, so we are giving this one and this part to this way we are going high. So then this delay will be there. But here t equal to 0 we need to start, but it is moving to t equal to 0.2 something. This point 2 delay is the rise delay.
Yes, sir.
That means we need to wait some time to reach from 0 level to 1 level. That is called as rise time delay, rise delay. Fall delay means it will take, it is in high position, one position, and it will take some time to reach low value. Okay, this is the low value we are reaching. Then there is a delay. I need to get the delay value at 10 seconds, but I am reaching at 10.2 something. Okay, so that delay is called as fall time delay. So both the delays we are having, because we are having capacitors having, it takes place to time to charge and discharge.
Yes, sir.
So your mobile is charging, right? The charging time is less, but discharging time, so charging time, less time only it is getting fully charged, and discharging time is
Very
getting
fast.
more. No, not fast.
Very good.
You are charging 1 hour time, but discharging will be
Yeah,
24
slower,
hours you are
slower.
taking. That is the delay will be more. Okay, so that is the fall time delay, and then turn off delay. So that means you are in high position, and then you are getting the output like high level to low level. See, while turning off your laptop, it will take few seconds. That is called as turn off delay.
Yes, sir.
Okay. Same thing I have explained: symbols, AND gate, OR gate, NOT gate, all these things. And then gate delays means delays we can represent. One time delay. So what is the delay we are representing means hash delay. Okay, hash 10 or hash 5. Okay, in the hash 2. In this way, the delay will be represented. Okay, in every transition you are representing delays means 3 times unit delays we are waiting, but sometimes we are representing maximum comma minimum delay. Okay, this is rise time delay comma fall time delay. So during rise time I am representing 2 comma 4. Okay, 2 comma 4 means, so rise time delay will be less and fall time delay will be more. Okay, this is the maximum delay and this is the minimum delay. Max comma minimum, in this way we are representing. Max represents the rise time delay and minimum represents that fall time delay. So 3 comma 4 you are representing. 3 is the rise time delay and waiting for high value and getting the down to low. Okay, that is the fall delay.
Yes, sir.
In this way, I am representing some buffers. We can store the data, right? So at that time, I'm going for represent some delays, and also we are having 3 time units delays. What are those delays? Means you are having rise time delay, and fall time delay, and then turn off delay. So turn off delay means it will show the time, 10 seconds it will take that. Or here I am representing 7 seconds. So in this 7 seconds your system will be turned off. That is the turn off delay. Okay. So normal delay you can represent that hash. Okay. So hash delay. And then if you are representing minimum and maximum hash, so hash you can take and 2 comma 3 or 5 comma 7. In this way you can take the delays. Okay. So these are the syntaxes: hash delay, hash r comma f. That means rise comma fault, and then r comma f comma t, rise comma fall comma turn off time. And also I told you, so minimum comma maximum, and then minimum means that is the fall time delay, maximum means rise time delay. So see, this is the type is the f maximum, f minimum. That means rise time delay, fall time delay, we are representing maximum comma minimum.
Yes, sir.
Okay. So these are the different delays in your gate level modeling. Okay, and then delay notifications we are representing here. So rise time delay minimum is 3, and then type is 4, and maximum is 5. And similarly, fall time delay minimum type is 5, and then maximum value. Okay, turn off delay minimum is 5, and then type is 6. After that, maximum time. So in this way, the delays will be represented. Okay. Same thing here also there. Okay, all the delays. So some examples are there. Okay, so buffer symbols and all these things. We are having low value means 0, high value means 1, unknown value means don't care. Okay, high impedance value is Z, and then gate notations like some single delay has 3, two delays has 3 comma 4, and then 3 delays like rise comma fall comma turn off time, and then delay notations like minimum time type is maximum. Okay, so then minimum 2, and then type maximum. So in this way, minimum type maximum, minimum type maximum, minimum type maximum. That means rise, fall, and turn off each value. Minimum means rise time,
Yes, sir.
maximum means fall time, type means turn off time. In that way we are representing. Okay, so these are the delays we are representing in our gate delays of the Verilog. Different type of delays we are having. Okay, turn off delay means I told you, so whenever you are going to off, so that is the turn off delay. Fall time means high level to low level we are reaching, that is the fall time delay. Rise time delay, rise delay means reaching from 0 to high, so that is the rise delay. Why it is repeating again? Okay, same thing, part 2 of delays. See, different values I am giving, and we are getting the different delay values. So, 1 time delay, 2 time delay, 3 time delay, all the values we are representing. Okay, see, input 1, and then 0, 1, 1, 0, 0, 0, all these values we are giving. And similarly, input 1, 0, 1, so in this way we are giving. And then delays, 3 time units delay. So at that time control signal will be 1. So the delay will be 3 times. At that time we are getting some unknown values. Okay, and then output 1 y1. So that y1 is your output. That means you are giving some values at time t0. You are giving some input value 1 and input value is 0. Okay, and then control value is 1. You are getting output value is unknown values. All are unknown values because the time delay is 0. At the time 3, it is reaches the time delay 3. See, it is reaching the delay 3, and you are giving inputs 1 and 1, and control signal also 1. You are getting 1's output.
Yes, sir.
Okay, so based on that delays, see 3 comma 4, rise time delay is 3. For that 3 delays you are maintaining, this is the 3. Okay, 3 delay you are getting 1, and then fall time delay is 4, right? So 4 means you are reaching the output value from low to high. So and then turn off time delay we can mention means that is also 5. See, you can see the output while giving that input value 10 time units delay. So that 10 time units delay means input is 0, input is 1, and control signal is 1. Okay, so at that time you are getting the output value is 1. That means you are giving to either NAND gate or NOR gate, you are getting the output like 1 or 0. Okay, check that conditions. Previously we have that, right? Data flow modeling. Data flow modeling means this is used for continuous type of assignments. Okay, whenever you are using continuous time of assignment, this data flow modeling is used. Okay, so combinational circuits we are having. That combinational circuits we are using this data flow modeling. Simply we are using assign keyword. So data flow modeling, how the designing is depends upon the data flow. So this data flow is defines that how your designing is flowing. Okay, from input to output, how it is flowing, that will be defined by the data flow modeling. Here we are using continuous time of assignment. In this continuous assignment, the keyword we are using called as assign. Assign is the keyword. In this assign keyword, see assign and then drive strength. Drive strength means either supply 0 or supply 1. See, drive strength indicates that to resolve any conflict, like you are driving some value, okay, some weak 0 signal or weak 1 signal, that strength we need to mention. Okay, drive strength and then expression. So expression means any value, that means A or B or A and B, that expression you need to mention. After that some delay and then constant values we need to express that. Okay, so drive strength maybe resolves that conflict when two or more assignments are same wire. Okay, if you are using same wire or net type, your strength may be in the same type of strength. That means weak 0 or weak 1.
Yes.
Both are same, having the same strength. Or supply 0 and supply 1. So both are having same strength. So that strength, it gives you the conflict values that you need to avoid with mentioning different strengths. And delays. Delays, you know that. So as delays we are representing that. Okay. See, I told you that. See, in the drive strength and delays are both are optional to use. Okay. So in design time we are not using, because simply we are assigning the statement like assign and output y equal to a and b. Okay. These two are both are optional. If you are assigning the statements, that is always active. That means whenever you are assigning the statement, see, this is a I1 XOR with I2. That means I'm assigning the result, the assigned result I1 XOR with I2. It is continuous type of assignment, that is completely active at the all the time. So at the time, so we don't want to mention either weak 0 signal or weak 1 signal and delays. So in the time of test bench time, you are representing the delays. But while you are going to design, you are not going to represent any delays, because delays are not synthesizable here. So see here, implicit continuous assignment and regular assignments. See how we are representing wire result we are taking, and assign result equal to x1 I1 XOR with I2. So these are the regular continuous type of assignments. And implicit assignments means, so you are taking wire as the input, and then without using any assign statement you are giving the result directly. Okay, wire is carrying the output directly. Okay, so this result I am not representing, but don't go for this. This is the best one. Regular assignment is the best one.
Yes, sir.
Okay. So sometimes if you are representing wire and result I1 XOR with I2, so then you can show, it can show that the result data type not found in your design. This type of error may come. Okay,
Yes.
so that's why don't go for this. So better wire you can represent wire result. After that assign result equal to I1 XOR with I2, I1 and with I2, I1 or with I2. In that way can represent. That is best way. Okay, delays you know, right? So how I am representing the delays, hash delay, rise time delay, fall time delay. Previous slide only we have explained all these things. In this continuous type of assignments, we have some delays. How we are representing, because in this assignment statement, RHS side and LHS side we are having. In this RHS side, we are using that variables, net type variables only we are using. And then LHS side, we are using some registers or variables. We are net type variables or register type variables or scalar type nets we are using. And then sometimes vector type nets are also we are using. So result is the y, okay, that should be assigned here. So this assign statement #5, this is the regular delay we are applying. And then while #5 result equal to I1 XOR with I2. So this is the implicit relay. Okay, automatically it is taking that. And then net declaration delay. Net declaration delay means so your input having the delay, and then after the value is assigned immediately, but result is getting after 5 seconds delay. Okay, so because you are applying delay to your variable, okay, whatever the result you have, that delay you are getting that some delay. That means output is assigned to result immediately, but result appears at the output side, it will take some delay. That is the net declaration delay, wire delay. Okay, so this is the basic example for your data flow modeling. I am taking the inputs I1 comma out I2, and then output. Whatever the results we are taking, and then this is the assign statement. I am representing result 0 I1 XOR with I2, no delay, and then some regular delay you are taking that. So assign result equal to I1 XOR with I2. Okay, so result 3 down to 0, I1 comma I2, some concatenation operation we are getting. Okay, concatenating means both the inputs are taking place here. See here, I am taking the 4-bit result here. Result 0, result 1, result 2 comma 3. So then fourth result is not there. Then you will get the high impedance value. Okay, that's what. So you are giving inputs unknown values. Always you are getting unknown value because fourth value is unknown, high impedance value. You are giving 0 0, and then I'm getting the output XOR gate 0, and then I1 is output 1 is 0, result 1 is 0, result 2 is any giving, you are giving any unknown value, you are getting the unknown value. So delay you are giving, right? So that delay is not getting at the 0th time. So that way unknown value you are getting. After that 0 XOR with 1. Okay, whatever the value you are getting, so zeros only. Okay, result 3 and 4 are also zeros only, and result 4 is unknown value, sorry, high impedance value, because not giving any inputs. Similarly you are getting the different values. Okay, fifth delay you are giving, then time to unit 6 means you are getting the value from the second output also. Result 1 also you are getting the output because delay is crossed, right? 11, 16 and 21 also it is crossed. Then all the cases result 4 should be high impedance value only you are seeing them. Okay, this is the module gate representation. Some all the gates we are writing here. Okay, this is the data flow modeling. How the data, most of the designers are using this data flow modeling and then behavioral modeling, because all the data flow modeling we are applying to combination circuits. Combination circuits means AND gate, OR gate, NOT gate, adder, subtractors, multiplexer, demultiplexer. All these are comes under in your combination circuits. Whenever you are giving input, you are getting output immediately. Right? That is the representation of data flow modeling. And then Verilog operators. What are the operators we are having? Different type of operators we are having. These operators are used in your hardware design course. Arithmetic operators, logical operators, equality, relational, and then bitwise, conditional, shift operators, reduction operator, concatenation operator, replication, and then operator precedences. So precedence means which one is having the lowest precedence and which one is having highest precedence. Unary operators are always having highest precedence, and then powers is the next precedence. After that, multiplication, division, and then modulo we are having the other precedence. and then like bottommost rule we are following, right? Brackets you are having highest priority, after that off is having the highest priority, division, multiplication, then after that addition, subtraction, all these things. Similarly, and then shifting operators, equality operators, and then bitwise and operation or operation logical, all these are concatenation, and then assign statements like plus equal to, that means incrementing, after that equal to is assigned, minus equal to decrementing, and then equality is applied. Okay, into equal to, so that means multiplication equal to. These are the arithmetic operators. Okay, so one by one we will go through it. First, arithmetic operators. What are those? Arithmetic operators, we have addition, subtraction, multiplication, division, modulus, and then power. What is the difference between this division and modulo? Okay, so division means, see, 7 divided by 2. So 7 divided by 2 means, so 2 is dividing the 7. So 3 times you are getting the quotient value here. Okay.
Yes,
So division you are taking means quotient value you are getting. Okay. Quotient value you are getting. And then 2 percentile by 7, sorry, 7 percentile by 2 means, okay, this 2 is dividing the 7 with 3 times. Okay, 6 is that, 1 is the remainder. Okay, this percentile gives you that remainder value. Okay, remainder value we are considering at the percentile time. Okay, division and modulus, this will be getting confusion, other things are same. And so in Verilog you are representing the power is double star. Sometimes we can also use cap to power. Okay, caps also we can use, but most of the times we can use the double star. Okay, 2 power a, that means it will use that powers of 2, 2 power 1, 2 power 2, 2 power 3, 2 power 4. In this way we will get the powers of 2 values. Okay, remaining things, you know, addition, subtraction, multiplication, all are operating same way.
Generally, percentage means they will multiply it 100, but here remainder is percentage.
Yeah. So that's what. In the behavior of operators, if we are having addition, that means binary addition. We are considering some binary addition. Suppose this is the simple example module name, and then I'm taking variables like a, b, and result. So this result holds the this variable result is holds your output, right? Right. So then this A is a verbose type. 4 bits is capability. 4 bits means 2 power 4. 16 values it will be stored. Up to 16 value it can be stored. That means 0 to 15. Any value it can store. Right? So then I am giving the value 4 tick D10 and then 4 tick D3. That means 10 value and then 3 value I am giving. So then result will be added like here. So this is all about is this design code or test bench code? This is design code or test bench code. How you know that? Is this design or test bench? So initial begin is there, right? Initial begin is not there in your design code. So this is always test bench. Okay. So this is the test bench because operators we are using in your you are using to pass the stimulus to your DUT. That's why it is a test bench code. Then result I am storing a plus b. I am displaying the result. That means 10 plus 3 13. Then your result is 8-bit result. It is capable to store 2 power 8 values. That means up to 256 values it can store. 13 is in within the range. That result will be stored in the result variable. A minus b subtraction and then into multiplication, and then 10 into 3 30. 10 divided by 3, quotient is 3 and then remainder is 1. This is the simple example for arithmetic operators. So in this we have different type of operating behaviors like binary addition. How we are converting this binary, 10 is that binary, right? So binary decimal value. For that I am going to write that binary value. So 1010. This 1010 adds with 3. Okay, so 0011. Then binary addition it is doing that. 0 plus 1 1, 1 plus 1 0. Okay, carry 1 1 and 1. 1101 means so that is 13. Okay, so in this way binary addition we are doing that. So carry will be generated means it will be forwarded to the next value, and then if it is overflow will be occurred means that will be considered as a fifth bit. Okay, so in this way we will consider that carry value. And then subtraction, while going to do the subtraction means you need to do the 2's complement. Suppose minus 3. This minus 3 you need to do the 2's complement. 0, 0, 1, 1 is the normal binary representation. 1's complement, how do you do that? 1, 1, 0, 0. Then plus 1 you can do that. So 1, 0, 1, 1. This is the 2's complement of minus 3. Okay. This value you need to add with 10. So 10 value 1010, and then minus 3 value is 1101. So 0 plus 1 1, 1, and then 1, and then 0. So 1 is there means in 2's complement you are neglecting this carry. You need to neglect this. So then we got the value 7. Okay, so in that way we will subtract the values. So subtraction by using 2's complement. So whatever the signed value is there, so you need to do the 2's complement, then add that value to the normal number, then you will get the actual result.
Yes.
Okay, and then larger multiplication like full precision protection like suppose if you are multiplying 2 into 7, these two are 4 bits, but your result will be 8 bit you are getting. At that time you need to give some bit will be large. Okay, so then your multiplication result should be stored in the larger bit you need to provide. That's why I have given the 8 bit here. So 4 bits I am considering at the addition time, subtraction time, and then same 4 bits will be appear at the output side while doing your subtraction or multiplication. Not a problem. Okay. See, and then integral division. Integral division it is storing that coefficient value. Okay, so whatever the fractional value we have that will be eliminated. Truncated means eliminated, and then 7 percentile by 2 means you are storing the remainder value. Okay, it gives the remainder value. And then exponential means powers of 2, rise to the powers of 2, 2 power 3. In that way we are having. Okay, see, we are having signed operations and unsigned operations. Unsigned arithmetic operations and signed arithmetic operations. Unsigned means it will store that 0 to positive values only. Whatever the positive values we have, those only it will store. And then signed means negative values are also there. That negative values how we are adding and subtracting means we are doing that. So 2's complement, then we can add that number, then you will get the actual result. See, in this flow overflow is there. So uh, bit width rules, how we are representing the bit width rule. Addition we are carrying the same bit width, and subtraction also same, but multiplication you need to give the more value, because you are multiplying with 4 bit values, sometimes you will get 16 bit values. That's why you need to give the full precision. And then division, same division value, and then modulus are also same width we are considering. There is no extra width we need. Okay,
Yes, sir.
so same thing, addition, subtraction, multiplication, division values, how it is storing that binary values, and then result value we are getting, and then bits should be varying here. Okay, so that is the thing we need to represent. So every time whatever the operations you are doing, the arithmetic operations, you need to give the result width compared to the input widths, the result width should be more. That is the better.
Yes, sir.
Then you can store aram say whatever the values you are getting, all the values will be stored. See, overflow concept means overflow you are getting, right. So sometimes two's complement you are getting the last values you are adding, then you are getting the carry value. So last bit we are getting the carry value. If your unsigned values, your carry will be taking considered as a value. And then signed values, you are neglecting that carry, because you are doing some cruise complement. At that time, whatever the overflow you are getting, that overflow will be eliminated, neglecting that overflow. These are the order precedence, like into, division, and then remind modulus is the highest priority. After that, addition, subtraction, and then less than, that means shifting operators like equality, not equality, case equality, bitwise operators. These are the precedents already we have seen, right, previous slide. And then arithmetic assign statements, continuous type of assignments. How we are assigning that continuous type of assignment? Sometimes we can use that procedural assignments, always at the rate star we can use. And then that star represents that each and every changing of variables, then your output will be changing. Okay, the output is depends upon the input variables. Here some values will be changing. And then inside functions are also we are taking functions, it will return some value. Okay, see, function name, that is the add function you are taking, and the input you need to mention input x comma y, and then output you need to mention add. So then return add value, one value it will return. Task never return any value, function only return that one value. Function doesn't allow any delays, task can allows the delays. Function it execute that zero time delay, task cannot execute that zero time delay, so it will have some delays. So that is the basic difference between the function and task. Someone is asking you what is the difference between the function and task. Function is executes at the zero simulation time, because function does not allow any delays. Function returns single value. So these three differences you need to say that. And then task, we are having delays, so that is not executed at the zero simulation time. And then task cannot return any value. Okay. See, division, it shows that value, unknown value, and then model is also results that undefined value, unknown value. If simulation may issue. Okay. See, here also arithmetic operation demo is there. Operators in that arithmetic operators performs mathematical operations on operands. Okay, these are the operands. These are the operators. Sum is an operator. A and B is the operands. Okay, so it will store the values A plus B, subtraction A minus B, multiplication A into B, division A by B, and then reminder purpose we are using A percentile by B, power purpose A percentile A star star 2. Okay, and then see, always not synthesizable, always not always synthesizable. Verilog is powers is always not synthesizable. Okay, sometimes it is not synthesizable. That's why some shifting operators they are using. And then negative operation we need to do the two's complement, all these things. So just execute this code. Okay, so what is the representation? Module name, input wire ab, and then output sum, difference, product, quotient, and reminder, power. Okay, all these are outputs we are considering. Okay. Tomorrow we will discuss this logical operators, and then equality operator, all these things. Up to this you can study. Okay, tomorrow we will complete that operators.